Welcome back to another lecture on macrofinance, or specifically on modern macro, money, and international finance. We will talk about lecture 2 about why we want to model things in continuous time, about optimization, consumption, and portfolio choice. This slide provides a quick overview of what we're covering in this lecture. First, I will provide you the big picture argument to why we should model things in continuous time. What things become particularly easy if you model things in continuous time, especially when in the model there's an importance of the portfolio choice. Then I will move on to explain the basics of the E2 calculus. We use this as a tool, so we need to know the basics, but we don't have to drive all the theorems behind it. And then we move to a single agent consumption portfolio choice. That's a partial equilibrium analysis, which just an agent is choosing his optimal rate of consumption and his optimal portfolio across various assets. And we do so by using various different stochastic control methods in continuous time. Traditionally, we can use the Hamiltonian-Jacobi-Bellman equation, which is very similar to what we typically use in standard macro, the Bellman equation approach. But in this lecture, we also focus on the stochastic maximum principal approach, the Pontryagin approach, generalized to stochastic environments. And we used the non-stochastic environment, the Hamiltonian, already in the previous lecture when we studied the continuous time version of a Kiyotaki-Moore model. And finally, the third method, which is another way to do things, is the Martingale method, which is closely related to stochastic maximum principle, is another way to get the optimal portfolio and consumption choice. All of these three methods, you can pick your favorite one, have advantages and disadvantages, but it's good to be familiar with all of three of them to make sure that we know everything. So first I want to say, okay, why continuous time modeling? The first thing I would say, that's actually, so often people say, isn't it much more natural to have discrete time because my GDP data come in every quarter? Why should I model continuous time? But first of all, I must say, yes, the GDP data come in every quarter, but it's not that the economy stops and at the end of the quarter, the economy is activity and then there's nothing and then it's always every quarter that there's some activity. The activity in the economy is continuous. It's just, we just aggregate it within the quarter and we come up with a number at the end of the quarter. Okay. So the underlying process is a continuous process. Okay. So, and then often you want to combine this data. If you do macrofinance, you have the GDP numbers, which come in every end of the quarter. And then you have some stock data, which come every day, or even intraday. So you want to combine the things which come with different frequency. And for this, it's a model is handy, which is a continuous time model, where you can have then calibrate it to models with different frequency. Now, the other thing is, if you think about consumption, it's the same thing. Consumption is not that you consume at the end of the month or end of the quarter. You consume perhaps not right now, but you consume a lecture. You consume something all the time. So essentially what we do is we just sum up within the quarter, and then we have a concrete utility function across the quarter. Okay. So the time aggregation is like when we say, oh, how much do we consume within a quarter, we just linearly sum it up as if the IES is infinity, and then across quarters we assume some intertemporal elasticity of substitution, but within a quarter we don't smooth. It's also a little bit unnatural, but if you think about continuous time in this sense, is more natural, where you smooth all the time. Why should you only smooth across quarters, but not within the quarters? Now, another argument why you should do continuous time is if you have problems which are stopping problems. When you say, I do something until I stop, I search until I stop. If you have discrete time, you always have integer issues with that. Should I stop this period or previous? And if you have a continuous setting, you get the time number, so I stop now. So optimal stopping problems are very natural. So that's another argument to go for things. But I'm not saying some other problems are more natural in discrete time. But I'm just making the case
you have to push back and say, what is about that? So essentially, and the other thing is, it has a sharp distinction between stocks and flows. So if you have a continuous time framework, a flow, each instant is a zero measure adds to the stock, but you have to integrate over it. It's a very sharp distinction between a stock variable and a flow variable. Because the flow variable is of zero measure in the stock space. And what we will see later on when we do our consumption choices, typically when you have a log preference in particular, the consumption choice becomes very simple. It is just time preference rate times your wealth. Okay. In discrete term, you always have to be careful, is it the beginning of the term period wealth or end of the period wealth? In continuous time, it's the same. So it makes it very simple. You don't have to worry about these things. And you will see, at the model, one model I will present later on, I can point you to a discrete time version of it, and then you can approximate it to get continuous time on it. Continuous time is precise. Discrete time, you have to do end period wealth, beginning of period wealth, you have to approximate one with the other in order to get the precise solution. Okay. Now, why continuous time modeling? Another thing is like E2 processes. Okay. An E2 process can be characterized fully by its drift and its volatility. Okay, so let me just spend a little bit of time. So you can have a lot of stochastic processes. An E2 process or class of E2 processes are very simple processes. We will work mostly with E2 process. Later we'll also do some jump processes. But in E2 process, you just say what's the drift and what's the volatility. So what's the drift? So what the variable x or the process change in the process, how much does it change, depends on the drift over time. So if the time changes, that's how much it drifts in expectations. And that's a Brownian, a standard Brownian. Okay, the DZ is a standard Brownian, meaning that it just has drift of zero. It doesn't drift at all. It's a random walk in a sense, but it's an infinitely often changing random walk, and the increments are enormous. Okay? And so you take a span, a probability space, which is spanned, let's say, by one Brownian. So let's suppose this is one Brownian, the DZ, that spans a probability space. Okay, this is driving things. And then you say, okay, there's another variable in this probability space that lives the process X, and it has a certain drift, which depends on time potentially, can also depend on what the current X is. So it could be a constant, so then it would not depend on this. Just the drift is 3%. And the expected return is 3%. So that would be a 3% drift. And the volatility is how much it loads here on this Brownian. The Brownian has a standard normal increment, so it's standard deviation of variance of 1, no mean variance of 1. If sigma is 3, it just means this is just 3 times its back. But this thing itself can depend on the x and the time as well. It could be that over time this becomes a bigger or smaller. Okay. So the E2 process is not very restrictive in a sense that you can still make it dependent on the x and t. If you make it a constant, then it would be much more restrictive. But who has worked with continuous time processes? So you have to. So I'm going too slow. Huh? Today is a little bit. There's not much math. It's more intuition. So characteristic of the full volatility dynamics in the probability space is given by the underlying Brownian. So I only need to know the drift specification and the volatility specification. And I would like to introduce some notation. What's the difference between arithmetic E2 process and a geometric E2 process? So essentially, geometric is like percentage growth, multiplied, so you have this x here still floating around. Or divide, if I divide through the x, that's a percentage change, dx over x. And this is an arithmetic change. Arithmetic is like plus minus a certain increment. The other one plus minus a percentage increase. And whenever it's an arithmetic one, mean or volatility loading, I make a subscript x. Whenever it's a geometric one, I make a superscript x. Okay, that's just notation. So that this mu subscript x is mu superscript x times x. Okay, superscript mu superscript x means it's a geometric mean. Think about percentage changes or volatility percentage changes. And we will see, I will show you in a minute that probability loading on a state space at discrete time, is more difficult to handle, and also in particular, getting conditional expectations will be much simpler with V2 processes. Okay. And because it will be just, we will see in a minute. Now, here's a question. So this is a Brownian increment here. If I have a Brownian increment, does it mean that every E2 process must have some normal distribution innovations? Stepping aside a little bit because the air conditioning is coming in on my neck. So let's suppose I have a process and I have mu. Let's suppose mu and sigma are constants. This dz has Brownian innovations. All innovations are Brownian. Oh, sorry, are normal distributed. They're Brownian, so the normal distributed. So then, if they're constants, they're also x. The innovations in x are also constant. Let's suppose if mu is 0 and sigma is 3, it means all the innovations would be normal, just with a standard deviation of 3 instead of 1. Okay. Now, if I make this mu and the sigma depend on x, it is still the case for any next instant. The innovation is always a normal. Okay, is a normally distributed. So if the next instant innovation is a normal, but for any dt delta t for any length period, it can be any distribution. Okay, so it's not a limitation. We're using a V2 process. It's not a limitation that I cannot capture somehow fat tails over a delta t period. How would this happen? For example, any innovation. So it could be, let's suppose I have a negative shock. dz is negative. X goes down, but then as x goes down, sigma is a function of x, so sigma goes up. So the next shock would have a higher sigma. And if x goes further down, the next shock has the x goes down further, the sigma would be even higher, then it would be even higher. So then I would get a distribution like this. You see that? Should I say this again? So for any instant, the next instant is always, the innovation is normal. But if I take any length of delta t, it can be any, it's not a normal anymore. It can be anything, and it depends how the sigma is changing as a function of x. Okay, particularly if sigma is decreasing in x. So if there's a negative shock, x goes down, the volatility goes up, x goes down, the volatility goes up. So I get so over a period of length of delta t, I get a much more fat tail distribution here. So I can capture time varying volatility there, and also time varying tail distributions as well. Okay.
So this graph is captured with a fixed t, right?
Fixed delta t, yes.
A fixed.
So I start at time 0, let's say, and then let's say delta t is 1. What's the distribution of x, the process x, at time 1? I go from 0 to time 1. Or this could be 0.01 or 0.001, any, but the next instant it's normal. So what is x and what's I know X now. What's the next X? How's the innovation distributed for the next instant? It's a normal. But if I take any finite length, not an instant, but a longer thing, finite length, it can be any distribution, depends how the sigma is specified. More primarily on the sigma, that's on the drift just moves the whole.
So this red arrow is.
No, there should be no error. There should be no error. It's just a distribution.
So the arrow does not mean
No,
time.
this arrow is so. This is a distribution at one point in time. So this is distribution at t plus delta t or 0.
It's like if you simulate 1,000, 10,000 times.
Yes, exactly. That's actually that's the mistake. I said that there should be no error. Good point. So given that you know already Brownian motion, so there's a binomial tree. You can think of Brownian motion is just the continuous version of our binomial tree. So think of it. So you go up or down. So this is an arithmetic one. If you go up or down, you go up and down the same increment. If it were a geometric one, it would be the same percentages up and down. It goes up again or down, and goes up or down. And if you have only 2 steps, you get the distribution something like this. Okay. Now what I do is I make, instead of 2 steps, I make 10 steps, but I make each step size a square root by 10 smaller. Okay. So I increase in the number of steps, but I shrink the step size. Okay. So instead of having this, I have now this thing here. So more steps with shrinking step size. So then I have much smaller steps. And then if I say what's the distribution, this is a standard Brownian. There's no sigma x, and so it's just sigma is a fixed number. But on the steps, but it doesn't move over time. And that's a function of the state variable. It looks like this. And if I go to N500, I get something like this. You see already the normal shining through. Okay. So this is for 500, and if I go to the limit, I get the normal distribution. So whenever have you done option pricing? Who has done option pricing? Cox, Rubinstein? No. Cox, Rubinstein. Essentially, the way they approximate the Black-Scholes formula is with a discrete time binomial tree. If you want to be, I mean, that's essentially the easiest way to understand. Now, I now want to show you why in a dynamic portfolio choice, what the challenge is in a discrete time model. Okay. So typically, what we want is we would like to do a portfolio choice across assets and across section, and also have a dynamic choice. Okay. So over time. So typically what we do in discrete time models, in simple models, is that when we would like to maintain the same distribution in the returns of a portfolio compared to the individual assets. Otherwise, we only can simulate, we can't do anything analytic. Okay. So if you do a static model like what the initial finance models did, the most models that do normal, not returns, normal payoffs, and constant absolute risk aversion utility function. So you have a portfolio which has each asset is a payoff which is normal, and a portfolio is a weighted sum of normals. So if each of the assets has a payoff of normal, the weighted sum of a normal is also a normal. Okay. And that's nice. And then I put in the exponential utility function, which is e to the power, beautiful second moment generation, and so forth. I get a nice mean variance representation of this thing. And so I keep all individual payoffs normal, which is a little bit strange for assets, for stocks, because they can't really go negative, but a normal payoff means it has to go negative. I just swallow this as a theorist. And then I do a portfolio, and it's also normal. I can put in my constant absolute risk aversion utility function. Whoops, I get a nice demand for things, a nice portfolio choice, everything's fine. Okay. That works for static models. Now for dynamic models, so because a portfolio is just a weighted sum of individual, that's what you see here. For dynamic models, it's a product of returns. Okay? So this, for the returns, I take the payoff, make it normal. Now, I typically would like to have, for dynamic models, is the return in this period times the return in the next period, the cost return 1 plus little r, plus times the return on the subsequent period. To do that, the product of normals is not normal. So when we do dynamic model, we do log normals. Okay? Because the product of log normals is a log norm. And then we do constant relative risk aversion, which is, c to the power gamma, and so forth, over 1 minus gamma. Then we can solve this nicely, in closed form. So typically we would like to have, for the many macro models, you have one risky asset, then you might have some debt contract, but the observation, everything washes out, it doesn't have any debt against himself. And then we can solve the whole thing. Okay. So for portfolio choice with many assets, we would like to have normal payoffs and constant absolute risk aversion. For portfolio choice or for dynamic models, over time, we would like to have long normal returns, so not payoffs, but returns. And because it's a product of them, and then have constant relative risk aversion. And so in discrete time, you have to make a choice. Do you want to favor my dynamic thing, or do you want to favor my portfolio choice? Then you say, let me switch off the portfolio choice. And that's what macro does mostly. Let's switch off the portfolio choice because it's not nice to handle. Let's get a bit of observation, and we have only one asset, 1 tree or whatever, Lucas tree. And then we can do this dynamic. Now the beauty of, or you do linearize. Now the problem with linearize, you kill all the sigma terms, all assets are equivalent, so you have to do, say, let's do second order approximation. So you don't kill the sigma terms, but you kill the time variation of the sigma terms. And then you log linearize more generally. The beauty of continuous time is that over this delta t period, as it goes shorter and shorter, it converges to a normal, and you can use the constant relative risk aversion for both portfolio choice and for the time dimension. Okay. And that's essentially the biggest advantage of this continuous time models. You can really model portfolio choice, but how can you have a macro finance model without portfolio? Making investment across different investment projects, across different assets is the key. So that's why it's very hard to do not the continuous time. Okay, do you see? Now, but I should also say in continuous time, also what you get a nice characterization. So what if you do discrete time, you go to the computer much earlier. So you said, I cannot do anything analytically anymore. I go to the computer, I go to numerical. But you cannot characterize many things. You can only have, here's my simulation. You cannot do so much analytically. And the beauty of what you get in continuous time in these settings is that you can get the wealth dynamics analytically, not analytically. So you have a better understanding how different groups' wealth dynamics moves over time. For the evolution of this distribution, you will have some Kolmogorov-Forward equation, Fokker-Plante equation, and that gives you a much nicer characterization how the wealth across different groups in the economy moves over time. Now, I should say, yeah, so one particular thing about E2 processes, and it's an advantage and a disadvantage. It's essentially a continuous process. So information arrives continuously in a smooth. It's not, nothing happens. Both suddenly there's an information event, and I learn something. You always learn continuously. So each part is a continuous thing. There are no lumps in information coming out. It comes out all continuous. And there's an implicit assumption in it, and it's actually a drawback that you can react. So there's always a little bit, a tiny information coming out, and you can always react to each tiny information. If you think it's binomial tree, you can say it jumps once, a big, or it jumps, every millisecond it jumps a little bit, tiny steps, and each time you can react to that. So you assume implicitly you can react all the time. Okay? So this reaction, that's an assumption that might be sometimes a bad indication. So just to be aware, you make certain assumptions which might not be sound. And so the beauty of this thing is that things never jump. So for example, if you make losses, you can delever. As you make losses in continuous way, you can delever. So your wealth goes down towards 0, but it never jumps to -5. Okay? So you always go continuously, and it's like the stopping programming. Everything is continuous. You say, oh, I do this, and I specify, and I never jump into the default region, because I might go to 0, and then I'm defaulting, but I never jump to -5. But sometimes I say, oh, you go bankrupt because there's a huge shock. In discrete time, you don't know where you jump to. So you jump from the current level to -5 or to -4, depending what the jump size is. And you have to specify all the time what is going on, whether you jump to -5, to -4, to -6. In continuous time, you only go to 0. You have to specify what happens at 0. Okay? But you don't have to worry what's going on in all the minus possibilities. And that makes the analytics much simpler. But if you want to have a model where you can jump and things, you have to introduce some jumps. Okay? You can, of course, put a jump process on top of it. And then you can put it in a clever way to keep the analytics still tractable. If you just put a jump on it, then you get the whole problem. So you have a discrete time, you get it back again. So you can use Levy processes with jumps, and we will have one lecture which is purely about jumps, where you put the jumps in it, but you want to be careful. Ideally, you want to put the jumps in where you always jump to the same place. Otherwise, it becomes very intractable very quickly. Now, I told you that in discrete time, taking expectations is often very tricky, or conditional expectations, while in continuous time it's not. So if I look at, so this V is a value function. And often say, what's the expected change in the value function? Okay, and this eta is my state variable. And in discrete time, then I have to say, oh, the value function next period can take on all these values. I have to take each along a grid, and I have to then specify and take the expectations over that, and I have to think, so that's quite involved. Now, in continuous time, if I'm in this eta world, then I know this I can approximate by, this is the eta formula. I will cover the eta formulas next time. That's essentially just the derivative of the V with respect to the state value, times the drift of eta, the state variable. That's the drift of this, so in expectations, plus some eta term. Okay. Remember this eta term. Why is this eta term there? Because the Brownian moves a lot around. Okay. So it depends whether this V function is concave or convex. I have to have a correction term there. So that's this eta term showing. But essentially, when I go then in the numerics and I go along the grid points, I only have to look, I'm sitting here, and I have to see, I might jump up one grid point, or jump down one grid point. If you have more grid points, they're very close to each other. So the approximation, we will see this of this V prime, essentially say, okay, I take the difference between 2 grid points and get the derivative out of that. And that's all. And then I get, because of 3 points, I can also take the second derivative out of that. So approximate the second derivative. So the first derivative, I can just say, okay, let's suppose this length, the grid point length is delta. So I take the V on this point minus the V on that point divided by delta is my slope. That's my approximation to V prime. And then I can do the same thing also to approximate using this. And then I take the difference between this 2 divided by this delta squared, and then I get this V double prime, an approximation. And that's all. If you do a discrete time model, I might jump all over the place and I have to specify the V function across all the, but here I just need to know what is the V1 level up, what is the V1 level down. And that makes the numeric analysis way simpler, okay, and much quicker. So
after we have seen why continuous time modeling is so much more attractive than discrete time modeling, we will now go in the basics of Ito calculus, stochastic calculus, before we study a single agent consumption portfolio choice in a partial equilibrium setting where the return and the price process are exogenously given. We do so using the stochastic control methods in continuous time. There are three different ways to do so. One is the standard Bellman equation approach, which we are familiar from discrete time macro. The second one is the stochastic maximum principle approach. And the third one, which is often used in the finance, is the martingale method. So we'll use all of these three methods to get familiar with them. So let's start with the basic Ito calculus first.
Okay, so here is the basic notation I would like to use as before. So we have an arithmetic Ito process or geometric Ito process. Whenever it's an arithmetic, the change in x, the stochastic process is given by a drift. That's the arithmetic drift, and that's the volatility loading, the arithmetic volatility loading. We use a subscript x. And whenever we have not additive, but percentage changes, geometric Ito processes, it's multiplied by x, and then we use a superscript x. So x superscript times x is x mu. So mu superscript x times x is actually mu subscript x. Okay, that's just notation. And we mostly exclusively use geometric Ito process. It's just a notational thing. Okay. So here is we had this last time already. We have the geometric notation in terms of the Ito formula. So we have if x follows an Ito process, is a stochastic process. F of x, of course, is also a stochastic process, follows an Ito process. It's just f prime of x times the arithmetic drift, which is the geometric one times x, plus half the second derivative times the volatility loading, the arithmetic one, but here's the geometric one times x squared. Okay, that's the Ito term. And that comes from the fact that, you know, the Brownian motion moves a lot around, and then we have the volatility term, which is f of x times the volatility, arithmetic volatility, the same. That's the standard Ito formula. So if I look, for example, often what we will do, we would like to know what is the margin utility. If I have a utility function like of this constant relative risk aversion utility function, the margin utility is just c to the power minus gamma. So if I take a derivative with respect to c, that's what you see. It's just c to the minus gamma to the power of minus gamma. And if I want to know what's the volatility of the C process, so I have the volatility of the C process, but I would like to know what's the volatility of the marginal utility process. Okay, and then you can see, then you get just minus gamma times the volatility of consumption C. So it's just applying Ito's lemma for this. So if we look at the stochastic discount factor, typically what we have is discounting with the time preference rate times the marginal utility at time t divided by the marginal utility at time 0. This is a constant, that's a constant. So it's the volatility of Xi is not, that will affect the drift is rho, but not the volatility. And it's only driven by the volatility of C. So I want to know the volatility of Xi, which is, you know, the volatility of C to the power minus gamma. And then I just apply this Ito formula, and then I get immediately the volatility of Xi is just minus gamma, the volatility of C. Okay, and that's essentially what we will use many, many times. And you will be so familiar with these things to manipulate this that it will be, as we say in German, it goes into your blood. Okay, then as we said last time, there's of course a Ito product rule. We have two stochastic processes, and we would like to know what is the product, what process is the stochastic process of the product. And that's just the drift of the first one plus the drift of the second one, drift of x plus the drift of y. And then you have essentially the covariance term, the Ito term. Okay, so if both processes move together at the same time,
then there will be a positive term. If they move in the opposite direction, that means y, for example, would load negative on the Brownian and x positive, then this would be a negative term and subtract something. Okay, and then you have also the two Brownians loading on as an additive way. And you see here also geometric notation. You see the beauty of geometric notation already. This is very simple given the geometric notation of the Brownians. And then you have the E2 ratio rule, where just not x times y, but x divided by y. And then you have similar. So instead of adding the drifts, you subtract the drift. And then you have to take also an E2 term, which is the volatility of y times the volatility of y minus the volatility of x. So that's, what's denominator is showing up here minus the volatility of the numerator. And then you also have this difference between the two. Volatility of the x, which is the numerator, minus the volatility of y, which is the denominator. Okay, so let's start with that. So here's our problem. We want to understand today, that's what we focus on today, a consumption choice, or it's like a consumption stream and continuous consumption stream and a portfolio weight theta. So consumption stream C and portfolio weight theta. Often we have only two assets, let's say the risk-free asset and a risky asset, just to keep it simple. It could be a whole vector, of course. This can be 100 assets as well. So that's the maximization. And we take as utility constant relative risk aversion with a relative risk aversion coefficient of gamma. And the net worth evolves according to the following law, that the change in the net worth, if you consume more, your net worth is going down. And then you get on your net worth, you get for what you put in the risk-free asset, let's say a fraction theta, you get the risk-free rate. What you put into the risky asset, you get the risky rate. Okay. So just to notice here, risk-free times dt, and this is DRA. So this is risky. It can be risky. Okay, you could have written here also DRT, but given that it's not risky, I have RT times DT. Okay. And then there's a solvency constraint that your net worth cannot go negative. Okay. If you have log utility, it's anyway not an issue. And it's essentially, you can also assume a no Ponzi condition. Typically, we assume that your net worth cannot go beyond a certain constant. Okay, might go negative, but cannot go minus 500 or whatever. So you have some beliefs about the risk-free rate. You have some beliefs about the return process of the risky asset. And we assume here it is just the risk-free rate plus the risk premium delta A, that's just a notation, plus some loading on this aggregate Brownian. There's only one Brownian. I shouldn't have said aggregate because there's no macroeconomy here. It's just one Brownian. You have to take the risk. And because it's a partial equilibrium setting, everybody takes prices and returns as given. Okay, so that's the problem that's the only problem we deal with today. Okay. So, and then there's a state space, and the state space is given by a state variable eta. Later on, this will be a well share, an endogenous well share, but today it will be just exogenous process. Okay. The state space is eta, and the risk-free rate can be a function of eta, and the risk premium can be a function of eta, and the risk itself is also a function of eta. Okay, so the risk premium is essentially the risk is part of the drift of the risky asset. So that's essentially what we have, and then we have, according the eta is evolving in this problem exogenously. Later it will be endogenously evolving a lot with a certain drift, and the drift itself is also a function of eta. So the drift of eta depends where in the state space you are. And why did I write it this way? Because it's a geometric, so this is a geometric notation. So there's this other eta here. Okay, I could have, and then there's the volatility loading, which is also can be a function of eta times the standard Brownian, which spans the probability space initially. Okay, and there's some initial state eta 0. You start out with an eta 0. So essentially, this decision problem has two state variables. One is the external state eta, and in this problem, it moves totally exogenous. There's an exogenous process given by this, and that exogenous is specified with drift and the volatility loading of this exogenous process. I mean, the process is given by the initial Brownian, but this is then also an exogenous process which drives the whole economy. In this world, it's exogenous. And then you, as the decision maker, of course, your net worth is also your state variable, how wealthy you are. And that's a little n. Okay, that's your individual net worth. So you have your own controlled state. If you consume more, your net worth is going down, going forward. And you have also the other exogenous, which is outside of your control. That's just given by this exogenous process eta. Later on, this will be also endogenous, but will be affected by everybody together. Okay, and this is your own thing. And then for each initial state, so for starting out with a certain initial wealth and a certain eta 0, we have a separate decision problem to solve. Okay, so that's the situation today. So here's a simple example where I say, okay, so this I can just specify these drifts and these volatilities, and let me just specify with a simple example. Let's suppose that the drift is actually, that's the geometric times eta, which is the arithmetic one. That's just our initial notation we had. It's just minus phi times eta. So it looks something like that. Okay. So why do we like that? Because it says, okay, it lives between -1 and +1. And whenever you're in the negative territory, the drift is positive. So the system drifts over there. And whenever it's positive, the system drifts back to 0. Right? So it can't get simpler than that. Okay. And then we also specify the volatility and say it's a quadratic in eta. So that's sigma, like a parameter sigma, 1 minus eta squared. And that looks like something like that. So how does the system look like? So the system drifts, it has very low volatility here, and then becomes more volatile and goes here, and it's very volatile here. And then if it will be thrown there, it becomes less volatile here and here, okay? But it drifts back in general towards 0, but it's also most volatile around 0, okay? So it can hang out here for quite some while. I mean, it will drift back very quickly because the drift is high, but it's not so volatile here, okay? And then mostly it will drift towards 0, but the volatility throws it away again from 0, okay? And later what we will do, I give you the drift of this thing and also give you this volatility. And I will ask you, not today, but after some lectures in this class, what will the station distribution of this eta look like, okay? So you have a system which lives like this with this drift behavior and with this volatility behavior, and then I let the system run for millions of years, and then I can tell you where on average is this eta, what's the distribution of eta over time, okay? And that's the stationary distribution, and in order to get from this drift and this volatilities to the stationary distribution, that's where the Kolmogorov forward equation comes in, okay? So the asset return, we just then assume, again, the return of the risk-free asset, let's say, is R0 plus R1. These are just coefficients times eta. We just assume certain parameters here. We just make it linear too. And the risk premium, we have a baseline risk premium minus delta 1 eta. So if eta is high, the risk premium is lower. If eta is low, risk premium is higher. Just assumed, okay, today. This will be all later on equilibrium outcomes, but for now we just assume it as functional forms. And then we have how risk is a risky asset. So if eta is going up, the risky asset becomes less risky. You know, it has a sigma 0, and then sigma 1 is a parameter which, or coefficient which, if eta goes up, the riskiness goes down of this asset A. Okay. So the risk premium is going down, and the riskiness is also going down. But that here we just take it for given. We don't solve an equilibrium, it's just for given. And I should say that the sigma, we always, the sigma eta is always positive But of course, in principle, could also become negative if the sigma 1 is very high. And here we assume all the parameters are strictly positive or weakly positive. Okay. So that's a problem. So this is just a particular example, but this was our problem today. This is a problem we want to understand today. Okay. And the way I would like to approach this, I want to solve this and show you the different approaches in 3 different ways. First is the standard one, which you typically do in macro, is the Bellman equation or Hamilton-Jacobi-Bellman HJB equation approach. Okay, it's just a continuous time version of the Bellman equation approach and requires an explicit definition of the state space. And I will also what there's a value function on it. You can think of the value function as an overall value function from the beginning, or a value function which also moves over time as time passes. Okay, and I will show that. And the way to solve this typically is you postulate, you guess a value function, and then you maximize your Bellman equation, plug it in, and verify that your guess was correct. And then once you have the correct guess, you solve for that. We will live mostly in this family of constant relative risk aversion utility functions, or Epstein-Sinn generalization, recursive formulations, and for these many things simplify, and that's why we can solve it further as well. So that's the first approach. And then we do the stochastic maximum principle approach, and characterize what's the difference. For you, you don't need to really know this approach in details. I just want you to know what the difference in thinking is. Okay, it's more the Pontryagin approach, in contrast to the Bellman equation. That's where the macro guys, here you have to specify essentially the whole state space and the value function across the whole state space. This is less demanding. You only have to specify along the equilibrium path. Okay, so it's less notationally heavy in a sense, and it's probably I think less notationally heavy approach, and it leads to the same thing. It's just a different approach. And it's, if you think about it, in macro, it's like this is a Bellman equation approach. That's more the Hamiltonian approach, generalized to stochastic setting. And then there's the martingale approach, which is a shortcut of this approach in a sense, and applies particularly well to the portfolio choice problem. Okay? And it yields some equations which you can easily interpret and can be linked to a linear factor pricing equations very easily. So it's not this approach. I mean, they lead to the same results. In particular, this leads to the same result as well, but it has a nice interpretation in this way. Okay, and most of the time we will actually use this martingale approach later on. Okay, because it turns out to be the simplest one. If you, for example, have a portfolio problem with a lot of additional constraints on it, like a cash advance constraint and other things and other Lagrange multipliers, sometimes you want to switch back to this one. Okay, but for our course, most of it will be on this martingale method. Okay, so let's just do the first one. So we have Hamiltonian Jacobi-Bellman equation, and I will then first derive the thing for this partial equilibrium setting, and then I look at 2 special cases with constant returns and time-varying returns. Constant returns just mean it does not depend on eta, on the state variable, and then time-varying returns, it depends on eta. Okay, so here let's set up a little bit more notation. Let's call the script A. So as I mentioned before, there is this economy-wide eta, which is beyond your control state variable, and then there's n, which is the state variable you can control through your control variable will affect the n state variable for you. Eta comes from outside. It's totally exogenous to you. Okay. And there's a set of admissible choices, and you choose the consumption stream. Essentially, you can think of there's a whole tree where the evolution of the state evolves, and you choose on each node of the tree, you choose the consumption and the portfolio shares theta. Of course, it's not a tree in a sense in discrete time. it is a Brownian. No? I choose constantly functions on this admissible set, and you have some initial conditions. So you have a set of policies from 0 to cap t that have to be admissible extensions of this set and subset of this initial set we have up there. Now, you define a value function as you typically define. You maximize the optimal portfolio choice, the optimal consumption choice within this admissible set, and this expected utility just discounted the discount rate of rho. And this you can easily verify. You can see, and that's just the analogy also from discrete time, that you can just, the value function is just you maximize this until cap t, and then from cap t onwards, you have done this falling from cap t to infinity. That's the value function coming. So when you do something from little zero, from 0 to cap t, and then at cap t, you will end up with some net worth, and the aggregate state will also end up at the exogenous, will also end up at sub cap t, and then essentially the value function captures all the future from that. Okay. In general, the value function, as I said last time, is from a particular point in time going towards the future. It captures all the future and collapses everything down to one point at that. That's the idea. And of course, where you end up, this depends on the choices of your portfolio choice and the consumption choice. The eta is outside of your control, but the NT is in your what you consume, and what your portfolio choices will affect future net worth you have. Okay, so ultimately, so let me jump ahead. That's what we get at the end. And you might have seen this already. That's rho times the value function is a maximum of U of consumption over consumption and the portfolio choice plus the expected change in the value function. Okay. And and I will show you in a minute, in discrete time, you get the same thing where you everything is written in terms of changes. No? Okay. So, but you have to derive this formally here. And I just give you the idea, just try to convince you that's what we do. So that's what we had. This is from the previous thing where I just move this guy on the other side, and then I get 0 is just given this. That's the guy from cap t onwards minus v0. This was this v0, and I move it over there. Okay. And then I do integration by parts, and I want to just replace this guy by integration by parts. This becomes this thing here. So I move essentially the term. This is the important term. I move this from 0 to cap t, which is just given by this thing. So you integrate, discounted the value function from 0. All the changes when you sum them up or integrate them up, then you actually get this part of it, and then this part of it to get the whole thing, which replaces with this part. So if you combine that, then you get this thing here. And all what you do then, so once you have this, you let this cap t go to 0. So this cap t goes to 0, and then you end up with this equation. Okay, so you make this cap t thing, which goes all the way here. You go this to 0, so you don't capture. It's just one instant left, so it converges to this, and then you have this guy left here. Okay. And then you get this equation here. So this we bring to the other side. So we have this equation here. So this, it looks like, sounds like it's an HJB. It's like a Bellman equation. Okay, HJB equation. So let me just say the interpretation of the stochastic version of the HJB. This is an implicit backwards stochastic differential equation, BSDE, for the value process of VT. So VT, as you move through this tree or on this Brownian, moves around. So what does it mean? So this different stochastic differential equation, backward and implicit. So it's stochastic So the equation for the stochastic process is not a deterministic function. So this Vt is not a deterministic function. It's a differential equation. So it relates different differential dTVTs to the process of Vt and other variables. It's backward, so it's forward-looking equations that must be solved backwards in time. So it moves forward, but from the future, you solve it backwards in time, and it determines only the expected time differential. So what matters is only the expected time differential, and that we mentioned this already last time. This thing is built if you have Ito processes, will be very easy to handle. Well, in discrete time, you also have expectations over changes in the value function. But you need to know the value function and across all the state space. Here, you only have to, once you apply some Ito formula, this becomes actually deterministic here. Okay. So implicitly, this term here is not explicitly solved for. Instead, it's part of a nonlinear expression in the right-hand side. And what the nonlinearity comes from this max operator. So you might think, oh, what's nonlinear here? It's actually all very linear, but the max operator makes it nonlinear. Okay. So essentially what it is, so a value function is something where you have something in the future and you want to summarize it in something today. Okay. So the value function, you look in the future, bring from the future back to the present. And so you do this backwards. Okay. So this is actually the formal derivation. I mean, not formal, the intuitive derivation, what's going on. I mean, you just need to know this equation. I don't want to ask you to derive it. There's an alternative way you can derive it more intuitively by saying, well, let me just do the discrete time, a version which you do all in macro, and just take the limit at the time intervals in the limit as they go to 0. Okay. So typically when you set up a problem in standard discrete time macro, you have the value function is just the maximum on this utility of this period's consumption plus beta discount rate, which is rho to the power e to the power minus rho, the expected value of the future value function. Okay. And you can write this for a time period. The interval is always, the gap is always 1, but you can also just say the gap is dt. Okay. Then I have to discount it to the power of rho dt. Okay, but now I don't say it's always 1 time period. So let's say 1 quarter or 1 year. Now I would have dt years. Okay, but then it's a delta t years. So I have to adjust the discounting too. Okay, so then this actually is evolving, is the consumption today, but then the time period doesn't move by 1, it moves by delta t periods. And here the change, the exogenous state variable also moves by the delta t periods. Now, what I can do is I can subtract beta this from both sides. So I subtract this. So it will subtract the beta here, divide by delta t and multiply by delta t. Okay, that's actually, I didn't do anything essentially. And then I get this expression and this expression. So because I subtracted that, I also have to subtract it here. There's this beta here as well. And then I have this expression here. Okay. I think Gautam, I'm right that there should be a delta t here as well now. So there's delta t here is missing. Can you keep a note? So I have to correct the slides. So this delta t is missing here. And then we let the delta t go to 0. And then essentially what you can see, this essentially becomes, or at least this becomes just this rho from that as delta t goes to 0. And this is this, and then this change here is just the change dv. Okay. And that's what we started out with. So this is probably the more intuitive way to think about it, but it just shows it's nothing extraordinary. The continuous time is the same as essentially the discrete time from deriving this. You went from here to here? Yes, yes. So I moved the limit inside. Yes. Probably, yes. So, but I don't know it on top of my head what regularity conditions there are required to. I mean, typically for all the problems we use, it's fine. You can do it. Just interchange it, yes. Yes. Yeah, so because we take the limit for the whole thing and then, so this is just an intuition that taking the limit. Yeah. Okay, so let's do this deterministic HJB equation. So next is transform the stochastic version of the HJB in the non-stochastic one. So the general idea is to use E2's lemma to express this term. And that's where also continuous time shows its benefits in terms of derivatives of the value function. Okay, so we take this thing, we don't take expectations. So typically in discrete time, you take the expectation of the changes and potential changes of all the value functions, probability weighted and all this. And we have to understand the whole value function across the whole state space. Now what we do is we express this whole thing purely as in terms of derivatives, okay, using Ito's lemma. Okay, that's a big advantage. So here's a question. So what is this thing? So this thing is a function of dv, and this is of n, and the exogenous. So I have the following four options, and I want you to tell me which one is the correct one. So this is just a drift term. No? This expected change in v is a drift term. Okay. So when I do Ito's lemma, there's always a drift term, and then there's a volatility term. But I only want the expected thing, so I can ignore the volatility term. So is it this one, this one, this one, or that one? And of course, you have two arguments here. So of course, I have to take a derivative with respect to the first argument and a derivative with respect to the second argument, just dt. Who is voting for this one? You're shaking your head. You see already, Ito's lemma is not showing up here, in the sense that we always said we want to have Ito's lemma applied. So Ito's lemma typically has an Ito term. Otherwise, it wouldn't be an Ito's lemma. So there's no Ito term here. So we need, this can't be right. No? So we need something with Ito's lemma with an Ito term. And that's the Ito term now suddenly, because the Ito term is showing up in the new drift term. No? So we have these drift terms here. Now we have, so A can't be right. So in B, we have now this drift term, this Ito term. And the question is, do we need the second derivatives with the volatility squared with respect to the first state variable, the personal state variable, and the aggregate state variable? And that's it. And then the other question is, do we also need some cross derivatives? Okay. And then we can, so is it the case that we need the cross derivatives? So half of this is Ito term half. And no, I can't even see what's the difference when, the bracket stops here. So there's the actual volatility terms, and then there's the cross derivative showing up twice. Okay. So let me give you the answer. Or does anybody want to give me the answer? Who is voting for D? Everybody. Okay. So let's go with majority in this case, even though normally should not. So essentially, you have in the Ito term, you need these volatility terms. You have two state variables. So you have the first volatility term, second derivative of the second term, and then you have two cross terms, and that's why this half is only applying to the first thing, and then the half times 2, and this half goes away. Okay. Now, so essentially we transform the stochastic version of the HGB in a non-stochastic differential equation. That's a trick you can do in continuous time. Okay, so something which is highly stochastic and you have to take expectations over, suddenly the expectations are gone. Okay, so what you need to know, so typically what we do is you have to replace expectations over a function over the whole state space. You have to replace it with derivatives, first and second derivatives. So the first derivatives are because of the normal derivatives, and the second one because of the eta term. Okay, so that's a big change between discrete and continuous time. Rather than taking expected values or probability weighted sums or across the value function across all states of the world, you take at this particular point, you take the first derivative, second derivative, and then you can get the expected change in the value function. Any function could be a price function too, no? But that's if you live in the eta world with eta processes, you can do that. Okay, and that buys you a lot of benefits. Okay, in terms of deriving things. So just the thing we just have, I've given you the choice. That's now we have transformed the problem into something where there's no expectations anymore. Okay, but I need to know, and we will have often we have to say, oh, we have to derive the second derivative here, and the second derivative with respect to eta, and the cross derivative, which appears twice times a half, and that goes out here. So for this problem, the drifts and volatilities, so let's figure out what's the drift. So we had this already. The drift of your net worth is minus consumption, the drift goes down. Remember, this is the arithmetic drift because n is in the subscript. And then you get the risk-free rate on the whole net worth. And then you get the risk premium on the risky holding. Theta you put in the risk-free asset, 1 minus theta you put in the risky asset. That's portfolio shares. And that's, you know, then it's also the case. The drift of eta is given by this expression here. And what's the volatility of your net worth? It depends on your portfolio share you put in the risky asset, and you multiply it by the amount of the volatility of the risky asset. Why is it multiplied by n? Because this is in dollar terms. So it's the amount of dollars you have in net worth. That's the amount of dollars you put into the risky asset. And that's the volatility. And of course, it's driven by this exogenous eta process. Okay. Questions? Yes. Oh, because we could have written here theta times that plus 1 minus theta, and then in brackets 1 plus delta A, because delta is only the risk premium beyond the risk-free rate. Does this answer your question? So that's just notational thing. This is just the risk premium. It's not the return of asset A. It's only the return beyond the risk-free rate. Yes. Yeah, consumption is the numerator. Yes, consumption is the numerator. Yes. Sorry. Yes. Okay. I shouldn't have said in terms of dollars. In terms of consumption numerator. Everything is in consumption numerator. Yeah. And let's suppose consumption is also $1 anyway. But everything is. We always do everything in consumption numerator. Later we will switch to a different numerator, like total net worth numerator of the whole economy. But for now, it's all consumption numerator. Thanks. This guy here? No, this is not. It's just you can just by introspection you get that saying, okay, this is for each asset the volatility, okay, per consumption unit, and how many consumption units do I put into the risky asset? That's my total net worth let's suppose the numeraire is apples. I have 10,000 apples, if you don't want to do dollars. And I put a fraction theta 30% into bond, 70% into the risky asset. So this is 70%. So 10,000 apples times 70%. That's how many risky assets I buy times the volatility of each individual asset. That's correct. No, this is the volatility of net worth. So because it says underneath subscript, that's the arithmetic volatility of net worth. So when the volatility of V, there would be a subscript to V. Okay, so the subscripts, everything matters quite a bit. So you always, whenever what variable is concerned is either a subscript or superscript, depending whether it's arithmetic or geometric volatility drift or volatility loading. Okay. Okay. So for this example, now I can plug it in. So I have this thing here. That's the more general. But for our particular example with only these two assets, and the asset return is just a function of eta in this particular way, I can plug it in and then I get this expression here. Okay, so I have this, the return, then I have the risk premium, and then I have the second derivatives, and I just plug in what I plug in these guys here. So I replace the drift of n, the drift of eta, the sigma squared of eta, and these guys here. And then I get this expression. So this is a nonlinear partial differential equation for the value function of as a function of n, my net worth, and the eta, the aggregate state variable. And again, I have nonlinearity because of this max operator. The max operator is here. Consumption only appears here. So I make the consumption operator here, and theta appears in this expression. Okay. The eta itself is totally exogenous evolving. So whatever theta I choose is not affecting the eta, okay, because it's outside of my thing what I do. Okay. Good. So let me do some two special cases, constant returns and time varying returns. Okay. Constant returns means the risk-free rate is constant and the risk premium is constant, and also the volatility is constant. So everything is just a very simple constant. That's the standard problem where everything is very much a constant. So to solve this equation, first let's solve the optimization problems, and it's very similar to what you would do in discrete time too. So the optimal consumption choice is the marginal utility of consumption is equal to the marginal value of net worth. Okay, if I give you one net worth unit in consumption numeraire, what do you get? How much do you get marginally on the value out of it? Has to be the marginal value of consumption. If you're not at a boundary, but if you're an interior solution, this has to be, the envelope condition is always holding this way. Okay, otherwise you're not at the optimal consumption. If you get more kick out of it by consuming more than having more net worth, which is like, essentially reflecting consumption in the future, then you're not at the optimum. And then you have the optimal. So essentially, where do you see that? You just take the first order condition here, and then you get these expressions here. Okay. Let me see, yes. So you take the use prime of C, and here the C goes away, you get the first thing here. And then you take the first order condition with respect to theta. So theta shows up here, and it shows up here. Now then you solve for that, you get this expression here. So, and if you look at this, what do you see here? Exactly, it looks like the relative risk aversion, and it's just to the power of -1. It's if you have to typically it's like, oh, the more risk, if you become more risk averse, that's the fraction you put in the risky asset. If you become more risk averse, so this is -1 here, you put less in the risky asset. And it depends if the risk premium is higher, so you put more in the risky asset. If the risk goes up, you put less in the risky asset. Okay, so it makes intuitive sense. Okay. So it's actually written here. It is like the standard mean variance portfolio choice. If you have a mean variance problem, like a standard undergraduate mean variance problem with normal payoffs, you would get a similar formula. Okay, so you get the same. That's essentially Merton portfolio weight. In continuous time, you get exactly what you would get in a discrete time with a portfolio problem. In a static problem, you would have, normal payoffs and constant absolute risk aversion utility functions. You would get a similar formula there. You get the expect risk premium on top divided by risk aversion coefficient, absolute one, times the variance of that. Here it's in continuous time. Of course, it's slightly different, so it's a relative risk aversion coefficient, but otherwise it's very similar. Okay, and so and of course it's not the utility function; it's the value function which matters. Okay, but you can see already that's connected here directly. Okay, Jan. No, it's because that's where the whole investment opportunity set and stuff like this comes in. Okay, so it's more dynamic in a sense. So if you were to have the static problem, then yes, but in this more dynamic setting, we will see in a minute that it will be actually capturing some dynamic effects in Mertonian hedging demand and things like that. Question? No. But of course, here it's very simple. Because, so I should have said here it's different because here the risk-free rate stays constant and the risk premium stays constant too. So there's nothing moving. So there's the state variable eta doesn't matter here. No, that's why you also see this whole thing simplifies. Let me just the eta. This term drops out because eta is not moving. This whole thing drops out. Oh, no, not these ones. Anywhere there's an eta derivative, they all drop out because eta is not moving. So there's no drift in eta, there's no volatility in eta, so these terms go away. So everything which has involved some moving eta is switched off because I made it a version where these things don't depend on eta anymore. Okay. So this was the most simple case. The risk-free rate stays constant over time. The risk premium is constant over time. Of course, it's a risky asset, but the variance or the standard deviation or the loading, volatility loading is also constant over time. Now, what I want to do now is that this is too simple. It should move over time. It's time-varying risk-free rate, time-varying risk in the system, and also time-varying risk premium. So it's a function of eta, but eta itself is still an exogenous process. Later on, this eta will be an endogenous process too. Okay. Okay. Oh, sorry. Yes. So before I do that, let's still stick with the constant return case, and we could now plug the optimal choices and solve the resulting ordinary differential equation numerically. Okay. So we take the choices, plug it in, and then can solve the ODE out of that. But we can also guess the functional form and solve it analytically. Okay. And so what's a guess? What's a good guess in this case is that you take the value function is just the per period consumption divided by rho. Now that's like if you take an infinite sum, you always divide it by the risk discount rate. So it's like it's a first good guess to take this. And we just have n times omega, and that turns out to something that explicitly assumes if somebody has a higher net worth, it scales up. So what matters if I double the n, I just multiply by omega, and then I get this value function. Okay, so and this omega is often referred to as net worth multiplier, or and here it's a constant, so it doesn't move around. And typically later it will be moving around, whether eta moves down or moves up. But here eta is a constant, so the net worth multiplier is also a constant. Okay. And so that's a constant positive net worth multiplier. It's like as if I say you have a net worth of $100,000, but I multiply by 1.5, and it's as if you have, consumption is more multiplied by this multiplier. And this will be later reflecting all this investment opportunity. So if investment opportunity moves around over time, and that's when the net worth multiplier, this omega, is either referred to as net worth multiplier or investment opportunity. As it moves around, it goes up and down. But goes up and down with everybody the same way if they all have constant relative risk aversion. But for this setting, it's just a constant. It's a fixed constant across time because eta doesn't move. Yes. Yes. That's a very good. Thanks a lot. So let me just repeat to be on the recording. So if you move rho on the other side, then we have essentially HJB expression, and saying that this omega. So now in the right hand side, it should be all the future utility stream, and the omega reflects then all the future as well. And then we can. So for our utility function, which is constant relative risk aversion, we have the special case with gamma equals 1, which is a log utility. And if gamma is not equals to 1, then we have non-log. So we can use that. And so we have, if you take log utility, so we have log of omega plus log of n minus log of rho, or that's just on the other side. That's equal to, if you plug in this optimal thing, so if you plug in these optimal levels here everywhere and do it also for the optimal, plug in the value function, then you get this expression here. Okay. If you stay with constant relative risk aversion, so you can do this at home, but take so this u replace now with omega n to the power 1 minus gamma over 1 minus gamma. So that's your u. And this rho, and also multiply it by rho, then you plug everything in from the previous solutions, like from the previous slide, you plug in these optimal solutions as well, then you get this expression here. And what I want to highlight is, in both of these cases, the n cancels out. Okay. So there's no, so you can see this log n, you can cancel out here. And here you can also divide through this. You see, this goes away, so the n goes away. Okay, so you can solve that, and the n doesn't really matter what n the net worth is. What does this mean? It means that this depends on this guess, of course, here. The net worth level doesn't really matter much. What portfolio choice you assume, and what consumption you choose, in a sense, the net worth level, it scales up nicely. Now, it might not scale up linearly, but it scales up nicely. So you don't have to solve for the n. And that makes, of course, the problem much simpler, because everybody, there's a rich guy, and then you solve the same problem for the poor guy, and it's a scale-up version of the other guy. Okay, and this makes, of course, the analysis much simpler, because now you have only one state variable, which is the eta, the exogenous state variable, and the other n. It doesn't appear yet immediately here on this problem. Okay, I'll put it differently. I can solve for the omega, then I just multiply by the n, and then I have this whole value function. Okay, so I can solve for this omega now, and then I can solve in a second step. Once I then have the n, I can solve for the whole thing. Okay, so in both cases, so we can therefore solve purely for the omega. Let's solve for the omega. Once you have the omega, then we plug in the optimal omega, and then we can use the n as 1. So the solution then is the value function looks this. That's what we postulated and guessed, and we verify that. And the optimal consumption using this thing here. So we take the first derivative with respect to n, and to use this functional form, we have this solution here for the optimal consumption. And for the optimal portfolio choice, we have this expression here. Okay. So with then we can solve for the optimal omega, constant omega in the value function, if gamma is not equals to 1, is given by this expression here. Okay. Yes, so that's, and if gamma is 1, I think it still holds. It's just this term dropping out. And we have here dividing by 0. So that's then some other log specification. So that's essentially the solution for the constant return case. Okay, and then we can give this some more interpretation. Let's try to understand this better, the consumption and the portfolio choice, in particular consumption choice better for this particular case. Okay, so essentially the reaction. So let me do the special case of log utility first. So let me first look at optimal consumption, then I look at optimal portfolio choice. Okay? So that was our optimal consumption, which is rho to the power 1 minus by 1 over gamma times omega to the power 1 minus 1 over gamma times the net worth. Okay. Now let me just say before I say anything, if gamma is 1, this is rho to the power of 1. This is omega to the power of 0, which is always 1 times net worth. So that means if you have log utility, you just have consumption is equal to rho times net worth. So this omega doesn't even matter for consumption. Okay, even more beautiful. No? I mean, in terms of solving problems. And when you start out with models, you typically start with log utility specification because consumption turns out to be always consumption is equals to rho times net worth. Permanent income hypothesis, net worth is all your lifetime income reflected in the net worth times rho, that's what you consume. Okay, it's very simple. Of course, there might be different guys with different rows, but it's still very simple to handle. Now, once you go to constant relative risk aversion, it gets more involved. It's also numerically then more involved, but in a model, as a first step, you always start, I would say, with log utility to solve that. And then once you've solved that, you later try the constant relative risk aversion model. And that's what we did, Julie and I, many times. So here, let's go a little bit more in detail. So this gamma is the risk aversion coefficient, but what really matters for consumption smoothing is essentially the intertable elasticity of substitution. Okay. And so the curvature of utility, if you have expected utility framework, the risk aversion coefficient and the intertable elasticity of substitution is linked 1-to-1. And the intertable elasticity of substitution, let's call it psi, is just 1 over gamma. Okay. So if psi is smaller than 1, i.e. gamma is larger than 1, when there are better investment opportunities, you would actually consume more and save less. So essentially you say, oh, there are better investment opportunities. I can consume already more because I have better investment opportunities. Why shouldn't I consume already today something about that? And I save less. Okay. Now, if psi is larger than 1, which means gamma is smaller than 1, then you have better investment opportunities and said, oh my God, I have this better investment opportunities. I should actually consume more and take advantage of these investment opportunities. So I consume less and save more. Okay, so it depends. It's very much a preference thing. And if you have psi equals to 1, the consumption wealth ratio is independent of the investment opportunities. That's the log utility specification. Okay, so that's what this investment opportunity omega or the net worth multiplier reflects. Okay, so but it depends whether this goes in one direction or the other direction, depends what's exponent, in particular what this gamma or this psi is. So why is there this ambiguous relationship? It's like the income effect and the substitution effect. So the income effect says, oh, I have this greater investment opportunities. I'm really wealthier today. I want to consume more. I'm richer, so I consume more and save less. And if you have a substitution effect dominating, you say, oh my God, this is great. I should substitute into this greater investment opportunities, actually save more and use these attractive investment opportunities and exploit that and consume less. And so it depends whether the income effect, substitution effect dominates, and with log utility, they'll just cancel each other out. Okay. So if psi is smaller than 1 or gamma is larger than 1, so you're more risk averse or you want to smooth more over time, and then the income effect dominates. If psi is closer to linear, so it means larger than 1, the intertemporal elasticity of substitution is larger than 1, so less curved utility function, then you want the substitution effect dominates. Okay, so you can see this very nicely from this formula. No, the psi is not the investment. The omega is the psi is just the curvature of your utility function. It's like the risk aversion coefficient. So risk aversion coefficient is how much you want to smooth things across states of the world. So if you're a risky outcome, how much do you care about the risk across state of the world and how much you want to smooth it? If you have very concave utility function, you really care across the states of the world a lot, but also because the same concavity is also across time, you also want to smooth across time a lot. Okay. So people with high gamma or low psi, low intertemporal elasticity of substitution, they want to smooth across time a lot. And if you have almost a linear utility function, you're fairly risk neutral or almost risk neutral, you're also willing to smooth across time very easily. Say, oh, I can just give up something today. And then you substitute in and say, oh, I take advantage of this investment opportunity. So this omega reflects these investment opportunities that come up. And how do you feel like I'm feeling very wealthy now? I want to consume some of it and smooth it across time and consume already today some. Or I say, oh my God, it's a great opportunity and I don't want to smooth so much. My smoothing force is not so powerful, but I want to exploit this opportunity as much as possible. Scale back today. It's worth smoothing, but it gives me more total income down the road. Do you agree? Or yes. Yeah, so this is moving around this investment opportunity. That's a function of, I mean, not here, it's a constant, but later it will be something which will move with eta, with the state variable, with the aggregate state variable. And it reflects, if omega, so let's suppose this whole thing is positive, and if omega it goes up, you want to consume more. Okay. If this goes the other way around, if it's negative, if omega goes up, you want to consume less. So that's what this formula represents. Okay. So what we do next, so combining the previous equations and dropping dt, so just notational simplicity and the time subscripts, you get essentially this equation we have. And the solution method solve the two-dimensional PDE for VT numerically, or you guess and reduce it, you guess to this formula and reduce it to a one-dimensional ODE of omega. Okay, so you can actually say, oh, I have to solve for the value function, which is a function of n in eta. Or I can say, I guess the value function, given my constant relative risk aversion utility function. Then the problem actually simplifies. And as we said, the n drops out. And then I solve for this omega as a function of eta. Okay, and then it's just a function of one variable. It's an ordinary differential equation rather than a function of two variables in the partial differential equation. It's much more difficult to solve. I can only solve it numerically. But once I guess this, I can reduce it to a one-dimensional ODE where instead of solving for V, I solve for omega, okay, as a function of eta once I have the omega, I can also, in the second step, I can solve for the net worth and then solve for the whole thing again. Okay. Okay. Now, I think I made a switch. So essentially, I made the switch already to. So this is implicitly, I made the switch already that omega is moving around. So, yeah, so now let me make the switch that omega is actually moving around, okay? So far I just assumed omega is constant, doesn't move at all. Now let's go for the more general case that omega, the state variable in the economy, is moving around, okay? Now consumption depends on my own net worth and it depends on the aggregate state variable, eta. It's still an exogenous process here. Now the only thing which depends on the aggregate state variable is this omega, no? Now this omega is a function of eta. So as for constant returns, but now the investment opportunities move around, they're state dependent, they're eta dependent, okay? Now the optimal portfolio choice, once I do that, I can do the same thing. And so I want, after using the guess from the previous slide, the optimal portfolio looks something like that. So you can derive this at home. So that's the myopic demand. So you see 1 over gamma, and then you see the hedging demand coming up here, okay? So that's like the same we had in the stationary setting, or if you what also referred to as myopic demand. And here you see the opportunities moving around here. So if you look at this terms together, can you see Ito's lemma here? So essentially, the additional hedging demand, which is this term here, depends on the covariance between the investment opportunity and the volatility of the asset, okay? Remember when we said, what is a covariance term? There's only one Brownian. It loads on the same Brownian. The omega loads on the Brownian and the A loads on the Brownian, okay? There's a probability space which is given by one baseline Brownian. And then the other variables are all functions of this baseline Brownian, okay? And if they are, let's suppose they have both positive sigmas, then they move in the same direction. If the baseline Brownian goes up, the A return process goes up and the omega process goes up. So you multiply the two sigmas and that gives you this covariance term, okay? Can somebody tell me why this sigma omega, that's the volatility of the omega, is the same thing as this term here? This omega prime over omega times sigma omega, sigma eta. Ito's lemma, very good. In this course, if I ever ask you something, 90% you're right if you say Ito's lemma. So you have really this thing here showing up here. And so because of Ito's lemma, so omega is a function of eta, okay? So eta is a stochastic process. Omega is a function of eta, so it's also a stochastic process. I can apply Ito's lemma on the drift term, but I'm not interested in the drift term, but the volatility term. It's just the first derivative, and then multiplied by underlying, so by this sigma eta, and because of there is this arithmetic, and I have to be careful as arithmetic with non-geometric one. So that's why this thing shows up here too. So that's essentially always, we will do this over and over again. But the hedging demand essentially, and I will show you next, the hedging demand is about how my future opportunity moves around. Okay, so I take some risk, I might have a negative shock, but when the negative shock happens, my opportunity might move around too. So not only what the cash flow pays off of this asset or what the return is of this asset right now, I have to also relate it how my opportunity moves around at the same time. So it could be that whenever the asset pays off very poorly, my opportunity is improving a lot. Okay, that's essentially this covariance here. Or it could be whenever the asset pays off very poorly, my opportunity goes down too. So then it would be, this would have what would be positive or would be negative. So that's where the investment opportunities Newtonian hedging demand comes into play. Okay, So it's not about myopically said, just look what's the return of this asset. I have to look more generally, when the asset pays off very poorly, how does my opportunity set look then right away on this state of the world too? Okay, for each state of the world, do they co-move or do they move in the opposite direction? And that's essentially what the hedging demand reflects. So here's the same thing again. So why should the variation in future investment opportunities be relevant for portfolio choice? There are two opposing motives. So if the investment opportunities are good, it is valuable to have any resources available. Okay, so you invest in assets that pay off in state in which the investment opportunities are good. So if you have an asset which pays off great, exactly when you then have a great investment opportunity, that's pretty good, no? So, but if the investment opportunities are bad, that's a bad time for investors and additional wealth is valuable. So you could also say, oh, if the investment opportunities are bad, that's a really bad time for the investor and I really value wealth in this, in this state of the world a lot. Okay. So and that's again, it's a little bit like what we had earlier for the income and substitution effect, just on the interaction between the payoff now and the looking forward on the investment opportunities going on from then. So there's for one instant, there might be a negative payoff, but then at the same time, there might be also a negative investment opportunity realization. So essentially have a portfolio, you can think of almost like a portfolio of things. I have the immediate payoff and I have an investment opportunity. Do they move, co-move or move in the opposite direction? And that's what just shows this up. So, and how much this matters depends again on your utility function. So 1 minus gamma, again, the risk aversion coefficient, relative risk aversion coefficient. If you have log utility, whoops, this whole term is gone. But not only is my consumption easy, my dynamic portfolio choice is also easy. Of course, it's also easy if the investment opportunity doesn't move. What happens then? Okay.
This zero.
Exactly. So this term is zero volatility. The sigma eta is zero, and so this whole thing is also zero. This was our previous case. Investment opportunity is not moving, and if gamma is 1, this also term goes away. Okay. But if investment opportunity is moving and gamma is 1, then I can treat it as a myopic demand of the portfolio. But if not, then let's say gamma is smaller than 1, so we're closer to risk neutrality between log and risk neutrality. So if investors are not very risk averse, they prefer to have resources available when it's a profitability to invest. So they say, okay, I really like it when the investment opportunity goes up. I want to have wealth then. Okay, if you're between risk neutrality and log utility. If you're more risk averse than log utility, then you really want to hedge against the bad times, okay? And then it goes in the opposite direction. And you see, it really depends whether this gamma is larger or smaller than 1, okay? And if you have a guy who is really very conservative, so his risk aversion goes to infinity, then what's also striking then is that he only cares about this term here, okay? Because this term goes to 0 and this term, this doesn't go to 0. The hedging demand drives everything. Okay. So I think this hedging demand, you should think a little bit, takes a little bit, but you say, the way you think about it, I have a risky asset, it pays off. It matters not only what my margin utilities at that state, it's also how does my risk investment opportunity co-move with that? Okay. Of course, you might also say, oh, most models I will be taught is on log utility. I doesn't care. But it's important to know this thing. Okay. So what determines the investment opportunities? That's what this omega function as a function of eta, when substituting optimal choice into HJB, n cancels out and we get the ODE, what we have seen, the investment opportunity, we can derive that. And we can derive then this linear. And often what will happen is that we want to solve things for the omega. So instead of solving the value function, so later on this value function, we have to go numerical. Instead of solving for this guy here, we solve for the omega. Of course, this more generally, this now for constant returns, but non-constant return is a function of eta. Omega will be a function of eta. We solve for the omega because it's easier to handle that. Okay. It is also less kinky, and typically we don't like things with kinks and stuff like that. So if I go back to our example, remember this was the example where the drift was, for low eta values was positive, for high eta values was negative, so it's drifting towards zero. The drift was linear in eta, and then there was this quadratic volatility. There was a lot of volatility around zero, but less volatility in extremes for simplicity. So we can solve for that. So here's this omega, and here's our consumption net worth ratio. And if you have log utility, consumption net worth ratio would be just rho. You would be just 2%. You take your total lifetime wealth and you consume 2% of it. Okay, permanent income hypothesis. And but here it's different. So when eta is low, then actually consume less, and if eta is high, you consume more. Notice omega is entering because we don't have log utility. So you see the omega, the investment opportunities for high eta values, you have higher investment opportunities, or net worth multiplier. So it's as if you would multiply the net worth at a higher value than you would with low eta values. And you might say, oh, what is really the big deal of this Bertonian hedging demand? Quantitatively, even though the risk aversion is 5, the difference is not, it's not so dramatic. You see, that's the difference in the thetas. So the myopic demand is dashed. The dashed one is the myopic one, and the blue one is the fully dynamic model. Okay, but it's the correct solution. So, and in certain environments, it might make a huge difference depending how the sigma A and the sigma omega co-move to each other. Okay. Remember what was the sigma A? I forgot now. The specific sigma eta was this hump-shaped thing, and I think sigma A was linear, so it was also hump-shaped. So, but it could be some other specification where the difference is much more dramatic. Okay. So that's how you solve this with the HIB approach. Very similar what you always did in macro. Just what's the big difference? The big difference essentially is that in the discrete time, you have way bigger problems solving portfolio choice problems. And you don't have this problem in continuous time. You can solve it. You see a lot of the things analytically. And one reason for that is we always have the expected change in the value function. The expected change in the value function, you have to take expectations over the value function over all states of the world, and take a probability weighted sum of this. Now in continuous time, you just have to deal with the first and second derivative of this thing. Okay, so you can make essentially what, of course, taking expectations makes it also deterministic, but you just deal with derivatives. That's one of the big insights in continuous time. You deal with much more with derivatives rather than taking expectations. Okay. Now, I'm running a little bit late. Okay. So this was the HJB approach. And so the next thing is the stochastic maximum principle approach. And so, well, given the time constraint, I will actually zoom in a little bit on the big picture. What's the big difference between the HJB approach? So again, you consider a finite horizon problem, and you have more generally could be a function of time, could be utility of function of time, it could be of the assets, some other processes which drive, and the X process is also by a drift, which is given by X and A, and this is a payoff flow, and this A is as a control, and X are the state variables. Okay, perhaps we should have used the same notation here as well. I guess we should probably change the notation on this to be consistent with the other notation. Now, the big difference is in the value function approach, you specify the value function across the whole state space. I give you an n and an eta, and you say, on what is the value function? Boop, that's the value. Okay. So even in some states of the world where you never go to, Okay, you have to specify everything. Okay, of course you have to specify not only the value function, but the whole functional form, everything across the whole state space. Okay, of course it's notationally heavy and it's also over specified because you might never end up there. So what you do in the stochastic maximum principle is much more fine-tuned. You only specify things along the equilibrium path. Okay, that's a big insight. Essentially, you don't have to specify things across all the state space where you might never end up to, in particular, not in equilibrium end up to. Okay. Of course, when you start solving this problem, you don't know yet where you will end up to, but the beauty of this approach is to say, let me just zoom in, specify conditions where we'll end up to, and these conditions, I will specify what I need, and so-called co-states of the system, and I solve them some Hamiltonian. Okay. So, and then you can, with this Hamiltonian, you get essentially some co-states of the system. The change in co-states is minus the Hamiltonian with respect to x, and x was our states, and then you have also the other co-state and with respect to dz or dc. Now let me change a little bit this to our problem, what we have. So the link to this might reflect on the screen when we record, but I think probably you need light, no? Otherwise fall asleep. Oh, okay. Yeah, good. Good. So that's so the link to the co-state variable. So I label now the co-state variable. So here initially I said, oh, this is co-state variable P and Q, just pick some names. But I label it now specifically called one Xi, and the other one I call var sigma times Xi. Okay. And you will see that this Xi will be the SDF, and var sigma is actually price of risk times the SDF. Okay. And once you label this, you will see immediately later on, oh, that's what it is. And so this SDF, the stochastic discount factor, is Xi, and then the loading of the stochastic discount factor on the Brownian, the dz term, volatility loading, is my var sigma, minus var sigma. So the co-state variable acts like a Lagrangian multiplier on the net worth evolution. So it's like I have a net worth evolution and I have a Lagrangian multiplier on it. This is this Xi, and it's a marginal time zero utility benefit of given agent AI, an additional unit of time t wealth. So that's what this SDF is. Okay, typically. I give you an additional unit of net worth, how much extra marginal utility or marginal value you get, discounted to time t. So I have to discount it by that. And later on, we will actually use the Martical method. We'll see later that this co-state variable is actually, the Xi will be the SDF, and as var sigma I will be the price of the volatility. So var sigma will be the geometric one, and var sigma times Xi will be the arithmetic one. So then I have to write the Hamiltonian this way. So here's my co-state variable on the net worth drift, and here's my co-state variable on the net worth volatility. It's arithmetic, so I have to multiply by this Ni and this Ni. Okay, so that's my Hamiltonian. Then I can plug in for my problem the drift and the volatility, and I get this. And then I take the first order conditions, and I get this first order condition, which is just, you see for consumption, and then I get the first order condition. My risk premium is just var sigma, which will turn out to be the price of risk, times the risk of on this plus this sigma q, the risk of the price q. This is a different q than the other q here. This q I have to fix. This is a leftover. This is this has to be one of the two state variables. So it's still the old q definition here. Okay, sorry. Can you mark this? So the I superscript. So are you on this line or this guy? That's the Brownian, the initial Brownian volatility. There's something missing here, so that's I will fix the slides. This guy here. Yes, so let me do the martingale approach. I just jumped ahead a little bit because the price of risk. So typically a stochastic discount factor is the marginal utility, it reflects mostly the marginal utility. Okay. And whenever you have a negative shock, marginal utility goes up. So it goes in the opposite direction. Okay, so you have a negative shock, marginal utility goes up. You have a positive shock, you become wealthier, marginal utility goes down because of concavity of your utility function. And so the SDF, essentially, this is the arithmetic loading on the stochastic on the DZ term. And this reflects essentially the marginal utility of this guy. And I want to keep the price of risk a positive number. It's just a normalization in a sense. So I just labeled these things so that I can interpret later on as this. This is just the SDF, and this is a arithmetic volatility loading on the DZ term of the SDF. So then you can, the co-state equation. So you have this is you have this Hamiltonian first order condition. Then there's the evolution of the co-state equation and the drift, and then under log utility, we will you can do the same thing. You can derive the same thing. What you get. So it's just applying the standard Hamiltonian tricks we typically do. You get this the same solution in the stochastic maximum principle as well. So as I said, I wanted to show you this, just give you the basic idea what it really does compared to the HJB approach. The HJB approach, you specify for every state of the world, you specify exactly what the value function is in all this. In the stochastic maximum principle, you zoom in and work much more with essentially Lagrange multiplier, and you work only along the equilibrium path. Think of these co-state variables as Lagrange multipliers, okay, on the net worth constraint. Now, what we will use is essentially a martingale method, which is close to stochastic maximum principle, but it's tailored towards a shortcut for portfolio and consumption choices, okay, in particular for portfolio choice. And the beauty is it yields an interpretable equations, and it's not so that the disadvantage is it cannot be applied so generally if you have a lot of other constraints in all this, because it's tailored more to this portfolio choice. And the way we do it, we postulate a stochastic discount factor process. We will use this over and over again. And then we work with that and close the model at the end. So let me show you the intuition for that. And again, like for the initial approach, with the HJB approach, let me just show you with the discrete time, and then we take the limit, how it works out in continuous time, because the martingale approach works in discrete time as well. Okay, you just don't use it in macro so much because it's more a finance tool. So the finance profession uses mostly the martingale approach. The macro profession uses mostly the HJB approach. Okay, but you can use whatever you want. But the martingale approach again zooms in more on the equilibrium conditions rather than specify everything across the whole state space. Okay. So let's do discrete time equivalent. So here is, I have this discounting here, and here I have a whole portfolio. So this is a portfolio weights theta. So it's a whole vector when it's bold times the price of the portfolio. This P is now the price of this portfolio. And that's the previous one, the price of the portfolio plus the dividends you get from that minus the consumption. Okay, so that's, think of this theta also includes, is now not only the risk-free asset, it is a whole vector of thetas. Okay. Now, this is just our standard Euler equation. You take the first order condition with one particular theta, you get the SDF times the price of an asset is just the expected value times the SDF next period from t to t plus 1 or this is from 0 to 2, so that brings everything back to time 0. So I could divide this through, but this is just the SDF from 0 to time t plus 1. That's the price of this asset next period plus the dividend you get. That's the X dividend price. And this is the dividend you get. Okay. That's a standard Euler equation. Just right here always marginal utility, and then it would be the same thing. So that's a marginal utility from consumption CT plus CT. That's a marginal utility of CT plus 1. Okay. So there is some marginal utility term missing here. So there's something. That's also something. This is only when people are risk neutral, this would be correct. Okay. If U prime is always the same. So the margin rate of substitution is just given by this expression here. So if you take this, so let me do the following. Let's suppose if there is no dividends here, okay, then you would say the process Xi times P, Ct1 plus P times 1. So the process Xi times P would be a martingale. Do you see that? So let's suppose there's no D, D is gone. Then this product here follows a martingale. That's what this condition says. That's like the Euler equation. Now that's only I have to find a trick to get rid of this D. Okay. So what I do is I say, well, let's suppose these shares are Microsoft shares, and it pays dividends. So I have to. This is actually not easy to price a Microsoft shares because it always pays dividends. But I can price a mutual fund which always takes the dividends and buys, once dividends are paid out, they buy more Microsoft shares. Okay, so I have a mutual fund. Whenever dividends are paid out, I buy more Microsoft shares, and then I have to price this mutual fund. Once I can price this mutual fund, and then I know what the dividends are, I can then go further on. So any of a self-financing trading strategy A, let's say, this is this mutual fund, where I take the Microsoft share, whenever Microsoft pays dividends, we buy new Microsoft shares. The value of this, the evolution of this value of this mutual fund times the SDF, this product here has to follow a martingale. That's what it says. And this is essentially just a restatement of the Euler equation. And this holds in discrete time. You take the limit, it holds in continuous time. Okay. Now, if you in continuous time, the whole problem is just rewritten this way. And I say, okay, let me take any self-financing trading strategy, like, you know, taking the dividends, buying more Microsoft shares, and take the value of this mutual fund. And let me say, take any self-financing trading strategy with a certain drift and a certain volatility. You live in a probability space where you can only load on this one Brownian with a certain drift and a certain volatility. And this is that's how this thing evolves. It's a geometric. So this is geometric drift, and that's geometric volatility. And I postulate that my SDF has to live in the same volatility space, probability space. So I have a certain drift and a certain volatility. Oops, this should be a DZ. Yeah, this guy here. Good. So then this has to follow a martingale. So the product has to follow a martingale. So I have an XA process and I have an SDF process. And the product itself is also a stochastic process. And I can E2's product rule. It has to follow a martingale. And that means it follows a martingale. I only care about the drift because all the volatilities, a martingale means the volatility term doesn't matter. No? So it follows a martingale. The drift has to be equal to 0. Otherwise, it wouldn't be a martingale. It would be a super or a sub-martingale. Okay. So, and what's the drift of this? So I have the drift of XA. So first of all, X has a drift of this guy. The drift of the SDF is mu of Xi. And let me call this minus Ri. Okay. Just a definition. It turns out this drift of the SDF is the risk-free rate. But you don't know this yet. let's say. So that's I call the drift of Xi minus Ri, then plus the drift of A, and then the eta term, which the sigma Xi, I call this minus var sigma. There's a dz term. Minus var sigma is the price of risk. Okay, you don't know this yet, but just I label it this way. Times the volatility, that's my eta term. And then some volatility term, but I don't care about that. It's just the marginal effect means the drift has to be 0. That's my condition. And then from this, I get this outcome. The expected return of any asset self-financing portfolio is equal to Ri, that was minus the drift of the SDF, times var sigma, that's the volatility loading on the Z term of the SDF, will be the price of risk, times the volatility of the asset A. Okay, now I say, let me price the risk-free asset. The risk-free asset has no volatility, so sigma A, this holds for the risk-free asset too. Sigma A is 0, and that means, okay, the expected return has to be this, so it means, oh, that's the risk-free rate. Okay. And if I say I would like to price asset A relative to asset B, what's the difference in expected return is equal to the price of risk times the difference in the risk. Okay, how much does asset self-financing portfolio A load on the aggregate DZ term, and relative how much does sigma B does the B self-financing trading strategy load on the DZ term? Okay, you can do this with any, and this could be the risk-free rate, and then you get just the expected return of asset A is equal to the risk-free rate plus the times of risk times sigma A. And sigma B will be 0 if it's risk-free rate, the asset B. Okay, and then you get immediate. That comes directly from, very simply, from this martingale feature. Okay, we will use this over and over again because it's just so simple and so quick to derive that. Now, what is this C for the case of, we can do a little bit longer, 2 more slides. Sorry. What is this C for the constant relative risk aversion case? So C was our stochastic discount factor. And of course, everything lives in this probability space driven by this one Brownian, this DZ Brownian. So the consumption drifts, that's the arithmetic drift of the consumption, that's the volatility loading of consumption. It lives in the same Brownian space. And I can say, I know that U prime, remember U prime was C to the power minus gamma, U double prime is this, and U triple prime is this guy. Okay, you can take the derivative on your own, just believe me. Now I can just use Ito's lemma. I say, so I want to have, this is my SDF. Now I know what the C process is. It's this guy here with geometric notation. And I then can say, okay, what is then the process of this guy here? Okay, and it turns out this is my favorite formula in all of finance. Just to let you know. Essentially, it just says, this is, if I want the drift of Xi, so where do you get this term here, rho, then if U prime, so I have this guy here. So, and I have to take derivative because I do U prime, first derivative of U prime is U double prime. And then I get the eta term of U prime. I have to take the second derivative of U prime, so it becomes U triple prime. So this becomes, that's the eta term here, minus this guy dz. So my SDF is given by this, with constant relative risk aversion is given by this term, and this is the risk-free rate, because the drift term of the SDF is the risk-free rate. That's what we have just shown. And you see it here, it's the time preference rate. What is this term called? That's the growth rate of the consumption. That's the Ramsey term. Now remember the Ramsey term? If the economy grows and your consumption grows, you will be wealthier in the future, because you will be wealthy in the future, not to consume now. I have to make you wait to consume in the future. So I have to offer you a higher interest rate. That's the Ramsey term. You know, when Ramsey, who developed this in 1927 or whatever, developed this Ramsey term, which is, you know, very important, for example, in environmental economics, where you discount for 100 years. If the future generations are so much more wealthy, you have to discount at a higher rate, because right now the marginal utility is much higher than it will be in 100 years when we're all so much more wealthy. And then this is a precautionary savings term. If your consumption volatility is very high, and let's suppose you have risk averse and you have the IES showing up here, if your consumption volatility is very high down the road, yeah, you want to save for precautionary reasons. So I don't have to offer so much interest rate. That's what's showing up here. Higher volatility in consumption. You want to save for precautionary reasons. The more risk averse you are, you want to save even more. If you're risk neutral, gamma is 0, then it's not showing up. But if you're more risk averse, then actually I don't have to offer so a high interest rate. Okay, the interest rate goes down, the more volatile consumption is. And this is the price of risk. The price of risk is given how much does your utility, marginal utility, move around. That we have done already before. No? If you have risk neutral, so gamma is 0, you don't care about risk. The price of risk is 0, and it goes up with gamma and the volatility of your consumption. If consumption doesn't move much, you can diversify for other reasons, and you don't carry much risk in your consumption, you don't get much price of risk. And you can generalize this to Epstein-Sinn, where Epstein-Sinn, you can separate risk aversion and the intertemporal elastic substitution. You see exactly this Ramsey term. There's the intertemporal elastic substitution showing up instead of risk aversion. And it's precautionary savings. There is a risk aversion term and one intertemporal elastic substitution term. Okay. Just think about this, fall asleep tonight with this equation. It is really a beauty. That's correct. Yes, so if there's no, let's suppose you have complete markets and no aggregate risk, so everybody can perfectly insure consumption risk, because if there's no friction in the economy, this would be 0. You have no aggregate, you have no idiosyncratic risk because you can insure it, no aggregate risk because there's no aggregate risk. This would be 0, and then your standard Ramsey terms show up. That's correct. Like in Iagari, Grosel-Smith, there's no aggregate risk, but you still have idiosyncratic risk. So these terms still show up. There's still a price of risk too, because your individual consumption risk, there's no guy who can perfectly smooth the consumption out. So let me just, so how do you really prove the martingale approach in continuous time? I just gave you this discrete time equivalence, and then we can take the limit, and then we get this martingale thing. And I gave you this intuitive approach. The way you really do it is a stochastic maximum principle, what we did before, and say, okay, actually, martingale approach is a special case of that. But you know, you can the calculus of variation. You can also use the calculus of variation. You distance yourself from the optimum by delta from the optimum at T1 and go back at T2, and you can show also, you can also derive some derivation why it is the case to get to the optimum. For you, the way I view it, it's a tool, it's a hammer. You just use it as you see it fit. I will never ask you prove the stochastic maximum principle or prove the martingale method, why it works. You should know it when it works and how it works. But you should know that, you know, one way to prove the martingale approach is using essentially stochastic maximum principle, and you can read up on that in the handbook chapter. So let me conclude with that. What we did today, we solved a partial equilibrium setting where either the return on the risk-free asset and the return on the aggregate asset was actually not time varying, or it was then time varying as a function of the state variable eta, but eta was totally exogenous. It was not an equilibrium solution. It was totally partial equilibrium. if the whole price processes, returns and premia were all exogenous. And then we solved it in 3 different ways. We solved, so you had your own net worth, which was you have a state control variables, and the control variables affect your own net worth process N. And then you have an eta process, which is totally exogenous. And we solve it with the Hamiltonian-Jacobi approach, Bellman equation approach. That's a standard macro way to solve it. And we have seen how in continuous time, taking expectations about future changes in the value function, you just replace taking averages or taking weighted averages, probability weighted averages across the whole state space. You replace it with the first and second derivative, and how you can solve and simplify things this way, and how you can, when you postulate certain value function for constant relative risk aversion, you can solve omega as a function of eta instead of the value function, and that helps you to think things. Then I gave you some hint what the difference between the HJB approach, prominent macro, to the stochastic maximum principle approach, where you actually do everything along the equilibrium path and work with essentially Lagrange multipliers rather than solving the whole global state space specification. And the Martingale approach is a more specific approach using essentially, you can almost say it's a subset of the stochastic maximum principle approach, where you realize that the SDF times the price process of self-financing trading strategy, this product follows a martingale. And in continuous time, that means the drift has to be 0. So you just use the E2 product rule, use the drift of this product and set it to 0 and then run with that. Okay. So that's what we did today. What we do on Wednesday is we look at the first model where there are 2 sectors and there's a well share, and this eta will be the well share between one sector relative to the other sector. Okay. Now this eta will then move endogenously rather than what we did today, where it was an exogenous process. So thanks a lot. So I see you on Wednesday, and sorry for running quite some time over. Sorry.